This is the first video in a series designed to help us understand and deal with controversies in science. As we'll see, you don't have to be a scientist or an expert in the field to resolve many of these conflicts as long as you understand the philosophical foundations of science and the fundamental rules of logic. So, that's what we're going to cover in the first two parts of this series, and then we'll apply these principles to some real-world controversies. At the core of nearly all philosophical, religious, or scientific questions, it is the truth that we seek. The process that we call science is a particular means of seeking the truth, and, as a result, we frequently hear statements like, "Science says this," or "Science says that," or "I follow the science." But a problem here is that people making these statements often don't even know what science is. In particular, people will often confuse what is said by scientists with what is supported by science. These two things may be quite different or even contradictory. So, before we attempt any meaningful discussion on what science says, we should first agree on what science actually is and the logical framework on which it is built. The most fundamental assumption in science is that the laws of physics are true everywhere and always. In the language of logic, this is called a universal statement. A universal statement is true only if it is true for all members of the set to which it applies. On the other hand, a universal statement is false if even one member of the set is contrary. If the set of applicability is large, like everywhere and always, it is impossible to prove that the universal statement is true because we can't verify it everywhere in the universe, past, present, and future. However, we only need to show one counterexample to prove that the universal statement is false. So this asymmetry between verification and falsification is the very foundation of modern science. Essentially, we demand that science works everywhere and always, and if it fails, we reject it. And that simple prescription is why modern science has been so successful. Of course, in order to test whether a scientific theory fails or not, the theory itself must be testable, and that is a requirement that all scientific theories must have. The 20th century philosopher, Karl Popper, referred to this feature as the principle of falsifiability, and simply put, it says that any scientific theory must allow for the possibility of something that we could observe only if the theory is false. For example, a theory which claims that a coin flip will always come up heads is a valid scientific theory because it is testable. If the flip does not come up heads, it is possible to observe the tails and falsify the theory. On the other hand, a theory claiming that unicorns prefer carrots over potatoes is not a valid scientific theory because it is not possible for us to observe the unicorn preferences. The theory is not falsifiable, so it is not a scientific theory. Therefore, the principle of falsifiability is a starting point for all scientific theories. We must be able to test the theory, and if the theory fails, we reject it. Simple as that. Now, a direct consequence of this feature is that induction has no place in the formation of a scientific conclusion. Induction is the process of drawing a conclusion based on one or more supporting examples. The reason why this is not valid is because, no matter how much evidence you might have to support a theory, it only takes one counterexample to prove that the theory fails. Because of this, our old friend, Karl Popper, considered the drawing of conclusions, based on supporting evidence, to be the very definition of pseudoscience. To illustrate this, let's consider two scientists, each performing exactly the same experiment in exactly the same way, and getting exactly the same results. The feature that distinguishes one of them as a scientist and the other as a pseudoscientist is in how they form their conclusions. The pseudoscientist will present only the evidence which supports the theory and, based on that supporting evidence, conclude that the theory is true. Meanwhile, despite a mountain of supporting evidence, the true scientist will conclude that the theory is false because of a small number of contradicting examples. Essentially, the pseudoscientist fails to apply the principle of falsification and forms conclusions from induction. One of the things you might have noticed here is that we never prove that a scientific theory is true. We can only prove if it is false. That doesn't mean all good scientific theories are false. It means that we haven't been able to prove that they're false, so we have confidence that they are correct. Take Einstein's general theory of relativity, for example. We've been testing that theory for over 100 years and it has not failed a single test. But it's still a theory. It will always be a theory and we will continue to test it. This brings us to the difference between scientific laws and scientific theories. Many people think that theories can eventually become laws. This is based on the misconception that you start with a theory and after lots and lots of rigorous testing, the theory eventually gets promoted to a law. But that isn't how it works. Laws and theories are fundamentally different things and serve different purposes. For example, way back in the 1600s, Sir Isaac Newton formulated his universal law of gravitation. This law was based on the observation that two massive objects will exert a force on each other proportional to the product of their masses divided by the square of the distance between them. Newton's universal law of gravitation describes the way objects behave, but it doesn't tell us anything about why they behave that way. That's why it's a law. It is an observable fact, describing what we see, even if it is a complete mystery as to why we see it. Meanwhile, about 250 years later, Einstein formed his general theory of relativity. In that theory, Einstein attempts to explain why gravity behaves as it does. That's why it's a theory. Newton's law tells us what, and Einstein's theory tells us why. There are many other scientific laws out there. We have Kepler's laws, Hooke's law, Newton's laws, Stefan's law, and the list goes on. For each of these laws, there is at least one theory trying to explain it. This is also why scientific laws usually come before the theories. Essentially, we observe a pattern of behavior, and a law is a very careful description of the pattern that we observe. Theories, on the other hand, are attempts to explain why the pattern exists. So, in simple terms, laws tell us what, and theories tell us why. And that's the difference between scientific laws and theories. Now, up to this point, we've looked at the philosophical foundations of science, the principle of falsifiability, and how induction can lead to pseudoscience. This is a good foundation, but, in order to deal with controversies, we need to go a little further. Controversy occurs when two sides deliver seemingly logical arguments, but arrive at completely opposite or incompatible conclusions. In our next video, we will look at how this happens and the tools we will need to resolve such controversies. In later videos, we will use these tools to analyze and resolve a number of modern-day, real-life examples. I hope you enjoy these videos and will subscribe or pass them on.